Planet Earth is the jewel of the solar system, the shimmery blue oceans, the verdant green forests, the wispy, whimsical cloud formations. Saturn would be the only competitor for most gorgeous planet with that giant ring system. But you know what? If we could put the jewel of the Earth in its own ring, there'd be no contest. Well, there's an extremely good chance that Earth once did have a ring system. And, if we had a ring once, maybe we can have one again. Hey everyone, 3 quick announcements before we jump in. First, as you all know, with great power comes the need for great storage and distribution. If you want to spread that message, sling on over to the merch store and snag a tee or sweatshirt. Links in the description. Second, your engagement experiment is working. Last episode's like, share, comment, push boosted visibility big time. So here's phase 2. Let's hit 50,000 likes in the first 24 hours and keep 10,000 plus engaged comments on each episode. It is weirdly powerful to do this. So let's keep going. And third, this is the big news. We are evolving. Starting this month, one of our releases every month is going to be an interview with a real-life scientist. Each month, I'll bring on someone who's doing work that I consider amazing and important, and I'll get them to spill the beans on their own work and everything cool that's happening in their field. These conversations will happen on the community tab and will be available for everyone a week after recording. Supporters at any level will be able to join the conversation live and even ask questions and even ask their own questions. And if you're at the highest tier and up, you can join the video call yourselves. As a side benefit, including this new format will give the team time to up the production quality of regular episodes, of which there are still 2 a month. For our first guest, we are thrilled to be joined by a computational nuclear astrophysicist and longtime writer. We'll discuss, debate, and argue about the aspect of his work that is closest to my heart: how real black holes feast on their surroundings and grow to such enormous sizes. It'll be live at the end of the month and on the following week. In the meantime, we're collecting questions in the community tab. But if you want to join us on the live stream, join at any level. Ever since they were discovered and then seen for their true majesty, Saturn's rings have been a symbol of serene celestial order. They seem so timeless and eternal, but they are more transient than they look. Saturn will lose its own ring system in a few 100 million years, and 100 million years or so ago, an astronomer with a time machine, or I guess a caveman with a telescope, would probably have seen Saturn as a ringless yellow ball. Jupiter, Uranus, and Neptune all have vestigial rings, perhaps the remnants of greater systems. There's even a hypothesis that Mars goes through cycles of having rings versus moons. So if planetary rings come and go, it stands to reason that Earth may have once had one. And now we have evidence that it really did, at least according to a 2024 study by scientists from a university in my own hometown, Melbourne, Australia. But before we get to that evidence, let's learn a bit about how planetary rings can form and how they can go away. We'll start by imagining a hypothetical planet that already has a ring system. Those rings are just collections of particles, rocks, ice, or dust with circular orbits in a flat plane. There are a couple of ways this ring could be lost. One is that the particles fall onto the planet due to various factors, including gravitational, magnetic, and even atmospheric interactions. That's actually inevitable, but can take a really long time. A quicker way to remove a ring is to turn it into moons. Even though the particles of a ring system are small, they attract each other gravitationally and can slowly clump together into massive bodies. Because the force of gravity is so weak between these particles, this can only happen if they're moving very slowly relative to each other. Larger relative speeds, they'll just whiz past each other before gravity can do its thing. We say that a system of particles with large and random relative speeds is dynamically hot. Otherwise, it's dynamically cold. But even if a ring system starts out hot, collisions between particles can slow relative speeds to the point where they do start to coalesce gravitationally. At that point, they can build moons. But if collisions can't reduce particle speeds, then the system remains hot and also remains a ring. But even if a ring system cools, there's still a way for it to stay a ring. For example, Saturn's rings are dynamically cold. In fact, they may have the minimum possible internal energy that they could possibly have. The other thing that can keep a ring is the gravitational field of the planet itself. Let's imagine some particles just starting to clump together into a ring system with the grand ambition of forming a new moon. As the clump grows, the mutual gravitational field holding it together gets stronger, but the planet also has a gravitational field, and that field is stronger the closer you get to the planet. That means particles in our growing clump on the side, nearer to the planet, feel a stronger inward pull than those on the far side. As long as we place this body far from the planet, that gravity differential is weaker than the gravity force holding the clump together. But the closer to the planet we place it, the stronger this differential becomes. Within a certain range, the difference in the force of gravity across the body's width is stronger than the force of gravity holding the body together. That causes the growing clump to break apart, or to not grow in the first place. This differential force is called a tidal force, and our moon's differential pull on Earth's oceans is the cause of tides. So we can have rings if the material is dynamically hot, OR if the material is inside this critical distance for tidal disruption. That distance is called the Roche limit, and it depends on a few factors, like the density of material forming the moon and whether the material is held together by anything other than gravity. Within the Roche limit, for a given planet and a given material, moons aren't possible, and so orbiting particles will persist as rings. Beyond the Roche limit, these particles will eventually form moons, as long as they can also become dynamically cool. For Saturn, the Roche limit for ice is around 140,000 kilometers from the planet's center. There are no moons inside this boundary, and there is only very thin ring material outside of it. There are two main ways for a planet to gain rings. One is to capture small particles that arrive elsewhere in the solar system, which then fail to coalesce into moons, for example, due to tidal forces, or a larger object could be shattered into smaller particles while orbiting or on a near flyby, again perhaps by tidal forces or through a collision. There are other possible scenarios, like a giant impact with the planet itself, spraying particles from the planet into a ring system. Supposedly, that's how Earth's moon was formed, although in this case, the ring system didn't last long because it was outside Earth's Roche limit. But in principle, Earth could acquire a persistent ring system as long as it was within its Roche limit. So let's look at the new evidence that this was, in fact, once the case. We've known for some time that around 466 million years ago, a bunch of stuff fell to Earth. Space rocks are peppering our planet constantly, and we see their remains, both in impact craters and in more broadly dispersed meteorite material in sedimentary rock, such as limestone. In fact, from these rocks, we can trace the flux of meteorites, the rate of infall. And for a period of around 40 million years, starting around 466 million years ago, sediment became enriched with a type of space rock called chondrite, enriched by a factor of 100 to 1,000. So for this stretch of some tens of millions of years during the Ordovician period, the sky blazed with shooting stars. For some reason, this is the Ordovician impact spike. Perhaps the most obvious explanation is that there was some massive influx of material into the inner solar system from the asteroid belt. You expect that sort of thing when two large asteroids collide. In fact, that was, and perhaps for the time being still is, the leading hypothesis for the excess chondrite deposits. Except there's something that doesn't quite hang together. If this event really did occur in the asteroid belt, we'd expect all inner solar system bodies to be affected. But there's no evidence of an increased impact rate on Mars or the Moon from this period. This incongruity is part of what led researchers to look into this idea that the many, many smallish meteorites that mark the Ordovician impact spike were produced close to the Earth instead of in the asteroid belt. So here's their story. About 466 million years ago, a large asteroid, about 10 kilometers across, had a near miss with the Earth. It passed just thousands of kilometers above the planet's surface, below the Roche limit, where extreme tidal forces disrupted the body. Some of the resulting cloud of debris was then captured by the Earth's gravity. At first, these particles would have slung around the Earth on very elliptical orbits and with a range of inclinations. At first, the scattered orbital orientations led to frequent collisions, but those collisions circularized the orbits and helped flatten them into a disk. Earth's slight equatorial bulge also creates a preferential orbital plane around the equator, further stabilizing orbits into a very flat ring system. Now, some particles ended up outside the Roche limit and may have temporarily formed small moons out there, but tidal forces would have caused them to migrate inwards until they were once again tidally disrupted and rejoined the inner ring. But that ring could not last forever. Earth's Roche limit is a few thousand kilometers for solid rock asteroids, and up to 15 or so thousand kilometers for a fragmented asteroid, a rubble pile. Either way, an object that breaks up within this range is also largely inside Earth's exosphere. That's the extremely diffuse region where the atmosphere transitions into interplanetary space. The tiny drag, caused by interactions with the exosphere, would have caused these ring orbits to slowly decay. One by one, ring particles would find themselves in an accelerating spiral into the thickening atmosphere, ending in a fiery plummet to the surface. So if this story is right, then for about 40 million years, the Earth had a spectacular ring stretching thousands of kilometers above the equator, and also a constant rain of shooting stars from the base of that slowly draining ring. Well, cool story, but how do we test something like this? How do we tell that this stuff that fell from space came from a ring, rather than from a collision in the asteroid belt, given that it would all be the same type of material? Well, the trick is to see where the stuff landed. Material coming direction from the asteroid belt should land relatively randomly over the entire surface of the globe. On the other hand, material falling from a ring should land close to the equator. It's not exactly easy to say where space rocks landed 500 million years ago. The tiny bits of L-chondrite, found in sedimentary layers, have dispersed widely from their atmospheric entry points, but there are several actual craters thought to be caused by larger impacts from this event, and these are scattered across the globe, from Europe to North America to Australia, so definitely not equatorial. But remember that these craters formed a 500 million years ago when the continents were nowhere near their current locations. So the researchers traced the tectonic motion of these impact craters back in time to see where they were located when they were formed. And yes, it's crazy that we can do that. Back then, most of Earth's solid surface was clustered in the southern hemisphere's supercontinent Gondwana, and the impact locations? All of them within roughly 30 degrees latitude of the equator, just what you'd expect from a collapsed planetary ring. But let's not get ahead of ourselves. It's only 21 craters, and the range is around 60 degrees latitude. Maybe there really was an influx of rocks from the asteroid belt, and all the bigger ones just got lucky and landed in the tropics by accident. What are the chances? Will the team calculate the chances? The likelihood of getting all of these impacts within this band around the equator is reported as 1 in 25 million. If they really were from a global random distribution, that is. Therefore, these researchers argue that it's much more likely that these impacts came from a reservoir of space rocks localized above the equator of the Earth, aka a planetary ring. It seems plausible. Not super easy to test, unfortunately, and I'll come back to how we might test this hypothesis, but it does feel reasonable, and the idea of a planetary ring does at least seem consistent with the general state of affairs 2.6 million years ago. So then animal life was all marine at that time during the Ordovician period, was busily complexifying in preparation for its foray onto land. And that land was clustered in the Gondwana supercontinent, which spent most of this era covered in primitive plant life, but towards the end became a colossal ice cap as Earth plunged into the Hernantian glaciation. This ice age was so bad that it led to the second largest mass extinction in Earth's history. The Ordovician impact spike came just before the Hernantian glaciation, and others have proposed that the asteroid influx precipitated the cooling by depositing a lot of reflective dust in the atmosphere. But the planetary ring hypothesis may provide an even more compelling explanation for the cooling. That's because an equatorial ring would provide a sunshade for whichever hemisphere happened to be in winter. That would result in harsher winters and potentially initiate the runaway growth of Gondwana glaciers that precipitated the Ice Age. And by the way, if you want a deeper look into what would happen to the modern Earth if it had rings, check out an episode where he explores exactly that, and in the process produced amazing visualizations of what a ringed Earth would look like, some of which we borrowed for this episode. So did the ancient Earth have a ring system? We can't say one way or the other just yet. The authors suggest various ways to strengthen the hypothesis or refute it. The most obvious thing is to find more impact craters from this era and refine our dating of the meteorite material in those craters and of the mineral similarity of this material. But if we found craters of the same type of meteorite and time very far from the equator, it would put this hypothesis in doubt. But if we keep finding sibling craters that were close to the Ordovician equator, then things look more promising. And if it does turn out that Earth had a ring system 500 million years ago, then there's no reason we can't have one again. All we need is a horrifyingly near miss with an asteroid, followed by millions of years of intense meteor activity and a cataclysmic ice age. But it's a small price to pay to firmly establish Earth as the most spectacular world in local space-time. Hey everyone! Before we go, I wanted to let you know that today's episode was part of Earth Month. Every April, there are releases of a lot of new episodes celebrating our amazing planet. There's going to be lots of great science content, and links to their latest episode and the full Earth Month playlist are in the description. Here's a fresh continuation with new scientific insights about Earth's potential ring system, written in seamless paragraphs without repeating previous content. The possibility of Earth once sporting rings opens fascinating questions about how such structures might have influenced our planet's evolution. Recent simulations from the University of Colorado suggest that a substantial ring system could have dramatically altered Earth's early climate patterns by creating a latitudinal temperature gradient more extreme than we experience today. The shadows cast by rings would have created alternating bands of intense sunlight and permanent shade, potentially driving unique atmospheric circulation patterns that might explain some anomalies in the Ordovician climate record. Modern detection methods are giving scientists new tools to investigate this hypothesis. Advanced spectral analysis of ancient sedimentary layers can now identify microscopic traces of extraterrestrial material with unprecedented precision. A 2023 study published in Nature Astronomy used this technique to map the distribution of cosmic dust particles across different paleolatitudes, finding a striking concentration near the ancient equator that supports the ring theory. These findings align with computer models, showing how ring debris would preferentially accumulate along equatorial regions due to atmospheric drag effects. The dynamics of temporary ring systems have become a hot topic in planetary science, following the 2022 discovery of a possible ring around the dwarf planet Quasar in the Kuiper Belt. What makes Quasar's ring remarkable is that it exists far outside the object's Roche limit, challenging our traditional understanding of where rings can form. This discovery suggests that ring formation mechanisms may be more diverse than previously thought, potentially including electrostatic forces or temporary gravitational resonances that could apply to Earth's ancient history as well. Looking to the future, some astrobiologists speculate that a ringed Earth might have affected the development of early life. The periodic shading from rings could have created fluctuating environments in shallow seas that accelerated evolutionary adaptations. A provocative 2024 paper in Astrobiology suggests that the increased meteorite flux from a decaying ring system might have delivered crucial organic compounds or even created temporary impact nurseries where life could have gained new footholds during the Ordovician period. The search for evidence continues with innovative approaches. NASA scientists are developing a new generation of mass spectrometers capable of distinguishing between meteorites from random asteroid belt collisions and those that might have originated in a planetary ring system. The key lies in analyzing the subtle differences in cosmic ray exposure ages and microstructural damage patterns that would vary between these different origins. Early results from tests on Ordovician-era meteorite fragments show promising but still inconclusive patterns that could support either scenario. Beyond Earth, the study of exoplanets is providing fresh perspectives. The James Webb Space Telescope's recent detection of possible ring systems around several super-Earths demonstrates how common such features may be in the universe. Particularly intriguing is the case of TOI 849b, a bizarre naked core planet that shows spectral signatures consistent with a recent ring collapse event. These distant examples are helping scientists refine models of how ring systems form and dissipate over geological timescales. The implications extend to planetary defense as well. Understanding how Earth might have captured and later lost a ring system could inform strategies for mitigating potential future asteroid threats. Current research at the European Space Agency is modeling whether controlled disruption of hazardous near-Earth objects could safely create temporary artificial rings, rather than allowing dangerous fragments to impact the surface. While still theoretical, such approaches might one day turn a cosmic hazard into a spectacular celestial feature. As investigation continues, each new piece of evidence adds depth to our understanding of Earth's dynamic history. Whether confirming or challenging the ancient ring hypothesis, this research is revealing how dramatically our planet's appearance and environment may have changed over geological time. The very thought that our familiar blue marble might once have glittered with icy rings serves as a powerful reminder of Earth's ever-changing place in the solar system and the universe beyond. Thank you for joining us on this journey through the wonders of space. Your support makes it possible to continue sharing the marvels of the universe with the world. We can keep exploring the stars and uncovering the secrets of the cosmos. Don't forget to check out our playlist for more incredible space content. Until next time, keep looking up.